So you see that the two common collector stages here plays a very important role here, and that significantly improves the gain, right? And so this is, I mean, apart from the common emitter, that is the main amplifying transistor here, that common collector amplifier. Apart from this, the common collector also has a very crucial role, and especially when the load ratio is very low, the two-stage common collector configuration and gives a big advantage, right, in overcoming those limitations with low input resistance. So the two common collector stages is, since this has this very important feature, and this is instead of you connect them separately, the two common collector stages are available in one single package. They are constructed as one single package. They are constructed and available in one single package, and this is called the Darlington pair because of their very desirable features that we look for, right, to transfer the signal from one circuit to another circuit. So we'll take a closer look at this two-stage common collector amplifier. What are the features and how we can use in our different applications, how they are useful in our different applications. So it is named after the name of the scientist. Darlington is the name of the scientist, and he was very early days of the transistor invention. He was playing with different configurations of the amplifier, connecting in different ways, and he suddenly found out that very interesting properties of this two-stage common collector amplifier. And since then, they have become another important device. So we have the two common collector amplifiers connected in series, and the input side we have the signal source, and the output we have the load resistance connected. Now, like before, we'll try to, determine the different parameters for these amplifiers, the input-output resistances, voltage, and current gains. Okay, so let's start with the input resistance first. So input resistance looking into the Q1, right? Into the base of Q1. So what we can write for Ri, the input resistance. Actually, we have already done that in our last lecture while discussing the adding the two common collectors and the output of common emitter. So if you can recall that, or you can just Hello.
Yes, sir.
What will be input resistance?
Sir, R pi 1 plus
R pi 1 plus
R pi 2 plus RL into beta plus 1.
Are you sure? Okay, looking from here to here is R pi 1, that is okay. When we come here, okay, we have this R pi 2 that will be reflected and gets multiplied by beta plus 1. But here RL is again in the emitter, right, of Q2. So that is not just. So what we do here, we assign another resistance here, we call it Ri2, okay. So this is the resistance here, right? That kind of an equivalent resistance, right? Ri2. So instead of the whole circuit, we can assume that we have a resistance Ri2, and that will be reflected into the base of Q1. And so we can write R pi 1 plus beta plus 1, because beta 1 plus 1 times Ri2, right? Now, what is Ri2, right? So that you need to determine. Ri2 is
R pi 2 plus RL.
R pi 2 plus
R pi 2 plus beta plus 1 RL.
Right. Now it will be multiplied by beta plus 1 and then RL. So overall, the input resistance expression will be R pi 1 plus, this is beta plus 1, and then Ri2, and we have Ri2 as R pi 2 plus beta 2 plus 1, that times RL. Okay. Right? So now we simplify this expression. this, if you multiply out beta plus 1 R by 2, and then we have beta 1 plus 1, and beta 2 plus 1 RL, right? Now what we see that this part will be much larger than this part because R by, assuming they both are same, so and this getting multiplied by factor beta plus 1, that's much greater. So and this we can approximate to beta 1 plus 1 R by 2. Yeah, that's what we have got here. And then we have beta 1 plus 1 and beta 2 plus 1 RL. Or if you can also express this as beta 1 plus 1 R by 2 plus and beta 2 plus 1 R, right? So here you see that this RL comes as the square, right? The RI, the input resistance RI, is proportional to beta plus 1 square, right? Beta plus 1 square. So beta is large, we know. So at least 100. Then beta is at least 100. Then beta plus 1 will be 10,000. Right? So that is how the common, and also alpha is getting multiplied by beta plus 1. So the two-stage common collector gives you very high input resistance, right? We get very high RI, right? Very high RI. Even for very low value of RL, it's just 10 kilo ohm, 10 ohm, you get 100K, right? More than 100K. And imagine if it is 1K, then how much you will get in the mega ohms, right? What is the input resistance for common collector? A single stage common collector.
Sir, R pi plus beta plus 1 RL.
Right. So this part is RI for single stage, right? Single stage CC amplifier. So what we can see here that RI for the input resistance, you can write it like this: the RI for two stage CC is much larger than RI for single stage, right? Common collector. So we have already said that common collector has high input resistance, highest among the three configurations. And if you add another common collector to that, you get very high input resistance, right? So this is one important feature of common collector, that it has very high input resistance. Okay, now we'll try to determine the R naught, the output resistance of the two-stage common collector. So what will be the output resistance? Can anyone figure out?
Sir, RE2 plus R01, beta plus 1 into R01.
Okay, so it will be the small RE2 plus
Plus R01
R naught 1.
is means the output resistance for the
Okay,
Q
so looking from here, the output resistance, we assign this output resistance R naught 1 and
divided by beta plus 1.
okay, so that will be R naught 1 divided by beta plus 1, beta 2 plus 1. So this is applying the resistance reflection rule. And what is R naught 1?
Sir, RE1 plus RS by beta plus 1.
Okay, not like this, right? Okay, so okay, so small RE1 and that plus RS divided by beta plus 1. So that's the resistance, output resistance, and also we can say that output resistance for the single stage. And now you substitute that here, we have RE1 plus RS and that divided by beta plus 1 and that whole divided by beta plus 1. And after simplifying this, we express like this: RE2 divided plus RE1 divided by beta 2 plus 1 and that plus RS that divided by beta 1 plus 1 and beta 2 plus 1. Now in this expression, if we look at this expression here, RE2 we know is small, and then we have this part, right? So where RE1 is getting divided by beta plus 1, so that will be much smaller than this RE2. So if you ignore that, we can approximate this expression as RE2 plus RS and that divided by beta plus 1, beta 2 plus 1. So that's how we can express this output resistance. And what we can say about this output resistance.
Sir, low output resistance.
How low?
Sir, only dependent on RE, R2.
If you compare with the output resistance of the single stage amplifier,
Yes, sir.
hmm, what is the output resistance for the single stage amplifier?
Sir, RE plus RS by beta plus 1.
Right. So that we have already written here at the beginning, right? So that is our the R naught for single stage, right? So RE plus RS divided by beta plus 1. If you compare with the output resistance for the single stage, what we see that we have same RE here, but RS is getting divided by beta plus 1 whole square. Right? So that reduces this resistance to a very low value, right? So we know that the output resistance of the common collector is low. It is the lowest among the three configurations. And when you add two common collector stages in cascade, it is even lower, right? You get a even lower output resistance. In this case, your R naught is proportional to 1 over beta plus 1 whole square, right? So you get a very low output resistance. So here we can write that R naught of two-stage common collector is much lower than the output resistance of single stage common collector. Is that clear, guys?
Yes, sir. Sir, there is another problem like in the previous class. We cannot see on the properly on the right side.
So how much you can see here? Let's say with the starting with the RI,
Sir, only beta 2 plus 1.
you can't see the RL.
No, sir.
Okay. So let me see which part I am. Oh, up to this much. Okay. Okay, your point is noted. Anyway, so you can understand what I have written here. So that will not be a problem, I guess. Okay, we have to move forward now. Okay, we keep on this same slide because then we don't have to draw again. Yes. So you can see this, right?
Yes, sir.
Yes.
Okay. Okay. So now get rid of this one. Okay, now we'll try to find the voltage gain. We're done with the input-output resistances. So for voltage gain, we assign the voltages at different points. Let's say these are base voltage VB2, this base voltage VB1. So the voltage gain, overall voltage gain V0 by Vs, and that we express like this. Okay. Now we just apply those formula, right, for the voltage gain for the common collector. So this is the voltage gain for the common collector Q2. This voltage gain for the common collector Q1, right, and that is the at the input side, the attenuation. So what we can write for the first gain expression, V0 by VB2.
Sir, RL divided by RE2 plus RL.
That's correct. So RL, that's resistance that is collected in the emitter, connect to the emitter, and the total resistance in the emitter circuit, that is small RE2 plus RL. Right? So that is the gain expression for the common collector from base to emitter. That is for Q2, and for Q1, what we can write? Hmm. So what is the load resistance for Q1?
Sir, Q2
Q2,
uh, or RI2.
right? The input resistance of Q2, right? If you look into the input of Q2, this RI2. So that is like the load resistance. So that's kind of, instead of RI2, if you assume that a resistance RI, instead of Q2, if you assume a resistance RI2 is connected here, so that will give the and I mean same effect, right? The equivalent. So RI2 will be kind of load resistance for Q1, right? So then applying that our formula for the gain of common collector. So that will be the resistance that is connected to the emitter, that is RI2 in this case, and that divided by, you have small RE1 plus RE2. And then finally, we have VB1 by VS. What is that?
Sir, Ri divided by Ri plus Rs.
Right, RI divided by RI plus RS. So that is our voltage gain. You see that we need just two steps, right, to determine the voltage gain if you know all these formulas. So that is very it's fast, straightforward, right? Now, what we can say about this voltage gain, overall the voltage gain of two-stage common collector, right? It is better if it is better than single stage, or if it is worse, if it is higher or lower. What we can say. For the two-stage common collector, what will be the voltage gain for the single stage? So if you look here that is our single stage, right? The Q1. If this is our load, right, and so that will be, this part will be our single stage common collector. So if you consider that this one and that single stage, it will be kind of we'll have RI2, then we have R. Okay, instead of that, I think we should consider this one. Let's focus on Q2. We have RL here, so the real RL. So RL divided by RE, RE2 plus RL. And imagine that we have a signal source connected at this end at the base of Q2, then we'll have this RI2 plus RS, right? So that will be for the single stage. Voltage gain for the single stage CC. Now compare this with this one. What are the differences, right? That is RL. So what is common here? This part and this part. These two are same, right?
Yes, sir.
And this looks similar to this, right? Just here we have RI, and here we have RI2. Otherwise, this RS is same, right? There's some similarities, but what is the difference here?
So the difference in the gain.
Difference in the value of RI, no?
Yes, sir. Yes, sir. Ri is much higher.
RI is much larger than RI2, right? It is almost beta plus 1 times RI2, right?
Yes, sir.
This RI, they're looking from the input, the base of Q1 is much larger than RI2, because RI2 is the resistance in the emitter of Q1, and that is reflected in the base and get multiplied by beta plus 1. So RI is beta plus 1 times RI2. So RI here is much greater than RI2. So when this RI is much larger, so this is, I mean, very close to 1, right? if Ri is much larger than Rs. With R is the same, and you get Ri being multiplied by beta plus 1, get a much higher value. So obviously, this expression, this Ri plus Rs will be much greater than or much closer to 1 than this part. Is that clear?
Yes, sir.
So this part will be much closer to 1. And if you look at the middle part here, right, that is the input resistance for the single stage common collector Ri2. And we know Re1 is low, right? So it is expected that Ri2 will be much greater than Re1. Right? Ri2 will be much greater than Re1. So this part will be also quite close to 1. And this part only that is common for both single stage and two stage common collector. This part is same, and we don't have any change. But this depends on the value of RL, how close it will be to 1. But apart from that, this common part, the other part, if you focus, we see that the what we have for the two-stage common collector, that factor will be much, that will be much greater what we have for the single stage common collector, because the Ri2 is much smaller than Ri. Right? So overall, this will be much closer to 1. And overall, the gain for the two-stage common collector will be much closer to 1 than the single stage common collector. Is it clear?
Yes, sir.
Okay. So what we got here for our, okay, let's get rid of this. So overall voltage gain, what we have much closer to 1, right? Overall voltage gain much closer to 1 compared to our single stage, right? Single stage common collector amplifier. So overall voltage gain for the two-stage common collector amplifier is much closer to 1 than the single stage common collector amplifier. Now let's see what is the current gain. Current gain denoted as AI, that is I naught by IR. So first we need to assign the currents. So we have the, let's say, current here is IB2 base current, And the current here is our emitter current of Q1, I1, and II is same as our IB1. So the current gain we can express as I naught by, we have, okay, we missed one here, IE2. I naught by IE2, and that times IE2 by IB2, and that times we have IB2 by IE1, and that times IE1 by II, which is IB1. So we can express like this the overall current gain. Now here I naught is same as IE2, and then we have IE2 by IB2. What is that? IE2 by IB2.
So beta.
Only beta.
Oh, beta plus 1.
Beta plus 1. IB2 is same as IE1, so IE1 by IE1. And here we have the same. Oh, this is a beta plus 1 again. Beta 1 plus 1. Okay. So these two will cancel out. Now we are left with beta 2 plus 1 times beta 1 plus 1. So what we get the current gain? What is the current gain now? Or what we can say about the current gain?
Here, it is squared, so squared.
What is the current gain for the single stage?
So only beta plus 1.
Right, only beta plus 1. Now for the two stage we get beta plus 1, like beta plus 1 squared, right? So it's a very high current gain. So these are the very important special features that the two-stage common collector has, right? It has very high input resistance, very low output resistance, a voltage gain which is much closer to unity, and a very high current gain. Right? Any question, guys? No question. So because of these special features, the common collector works as a much better voltage buffer. Two-stage common collector works as a much better voltage buffer than a single-stage voltage buffer. Right? A voltage buffer should have a voltage gain of 1, right? The input resistance should be infinite, and the output resistance should be 0. So that is what we call the ideal voltage buffer. Now, two-stage common collector has an input resistance which is much larger than the single stage, right? Two-stage common collector, right? The Ri is much larger, right, than Ri for single stage. The R naught much smaller, right, than R naught for single stage. Right? And voltage gain is much closer to 1. Right? So all these features, right, they make the two-stage common collector a much better voltage buffer than the single-stage common collector. Right? It is more effective in minimizing the loss at the input side and also more effective in minimizing the loss at the output side, more effective in transferring the signal right from input to output side and with minimum loss. So it works as a much better voltage buffer, and because of that two-stage common collector, also known as the super follower. The voltage buffers are also known as the voltage follower, right? Voltage buffer, they're also called the voltage follower. Why it is called the voltage follower?
So it has unity gain.
So what? Why it is called the follower? Then it should call unity or what? Unity voltage gain. It's called the voltage follower. But what is the significance of this follower?
So it transfers the input signal to the output signal as it is. No shifting, no amplification.
But why the term follower?
Uh, so no idea.
Because the output follows the input. That's why voltage follower. Right? So if you have Vs here, that is your input, right? And then you have the load RL, right? And you have V0, right? So V0, this output voltage will follow your input voltage Vs, right? If you're an ideal voltage buffer, then you see Ri is infinity, so current is zero, right? There is no current flowing and voltage drop will be zero here. So you get the full voltage Vs here, right? And unity voltage gain, you get the same voltage Vs, right? So V0 is following Vs. See, ideal voltage buffer, there's no loss, neither at the input side nor at the output side. So that's why the term voltage follower. The output follows the input. So ideal voltage buffer, the output will be exactly same as the input, right? The Vs. But if you add a single stage common collector, it has high input resistance, right? So it will limit the current, but still there's some current and there is some loss. And so the voltage that you have here, not Vs, but you have Vi, right? So it will not, you have a non-zero voltage drop here, and Vi will be less than Vs, right? And similarly, there is some output resistance side, there will also some loss here. And so V0 will be less than Vs, right? So it will lag behind the input voltage. Output will not be exactly same, right? But if you use a two-stage common collector, right, two-stage common collector, you have very high input resistance and current will be very low, right? And maybe the drop, the loss that we'll have here will be negligibly small, right? And it will be very much closer to Vs, because Vi will be much closer to Vs. And also this, the gain is also very much close to 1, much closer to 1. And so the voltage here will be very close to this voltage. So output will be closely follow the input, right? So that's why I call this super follower, right? The two-stage common collector, they are also known as the super follower. Is that clear?
Yes, sir.
The two-stage common collector, they are also shown like this because they are constructed and available commercially as one single device, right? Like transistor, right? The transistor is a single device. And two-stage common collector, they are also constructed as one single device. So they have these three terminals, external terminals. This is our base, and this is our collector, and this is our emitter, right? And that is called the Darlington pair. Right. So that is how it will look like. So there is one single device, right, working like a single device, and it has three external terminals, right, like transistor, base, collector, emitter. It has all those same three terminals, but very special features. It will have very high input resistance, very low output resistance, and also very high current gain. Right? This is a very important feature. And because in many applications, you need high current at the output. I like in speaker, right? If you are using a loud speaker, and they need large power and large current, right? So in those cases, in the Darlington pair solution, because it is very high current gain and you can supply high current to the load. So not only as a voltage buffer in situations where you need large current for the load, you also use Darlington pair, right? The two-stage common collector instead of the single transistor. Any question, guys?
Sir, from the previous circuit with the RC1, sir, what will be the gain expression? Overall gain expression, sir.
Not this one, right? The last class.
Yes, sir, last class.
This one.
Yes, sir.
So in this case, you see that the load resistance, you have minus GM, right? For common emitter GM2, and then RC will be in parallel with RI3, right? RC will be in parallel with RI3. But since RI3 is very large, right? It's several hundreds kilo ohm, right? Hundreds of kilo ohm. RI3 is much larger than RC. So you can also use approximate to minus GM to RC. Right? So this is how, right, you can make the gain independent of RL, because now in this expression you don't have RL, rather you have RC, right? And you can choose appropriate value of RC to fix the gain, right? And that will fix the voltage, right? So even if you change the load, right, to some extent, the voltage here will remain same, you get the same voltage at the output. Is that clear?
Yes, sir.
Yeah, so that is how you can fix the voltage and fix the the power that the load will get.
Sir, what will be the output resistance R naught for this one?
Same as what we have discussed before. In this case, you have here you have RC, and also you have a small R naught, right? These two will be in parallel, right? Instead of RS, right? Instead of RS, you will have the R naught in parallel to RC. So if you go back to our previous our today's lecture slides. So here we had RS, right? And RS is here at the base of Q1, right? In that circuit, what we have instead of RS, we have RC, and that is in parallel with the small R naught, the transistor Q2. Right? So instead of RS, you will have this RC in parallel with R naught. If R naught 2 is, this is much greater than this, you can just approximate this to RC. Right? So instead of RS, you will have RC. Is that clear?
Yes, sir.
So you can also do this step-by-step derivation for that circuit and see how it is coming out. Should be same what I have said. Okay, so that will be all for today, and time is almost up. We'll hopefully continue with our discussion on multi-stage amplifier in its class as well. And then next week, Thursday, we'll have our meet around in the evening, around 6 or 7.